Good afternoon, everyone. My name is Daniel, and I'll be presenting on Class 1 Quantum Cryptography today. Today I hope to talk a little bit about classical cryptography and just some of the basics, as well as implementations of symmetric and asymmetric keys, which are basically the two cornerstones used in cryptographical communication. And then I'll go into the quantum regime, where I'll talk about qubits for a little bit and try and give everyone a good review about how that works. And then I'll talk about the phenomenon of quantum speedups. And then I'll talk about the implications of Peter-Shor's algorithm and talk about quantum key distribution protocols that are proposed. And I'll conclude just by introducing the concept of a quantum network. So to motivate cryptography, we want to know what it's used for. And basically, it's used for when you're communicating with someone else. Typically, we call these two people who are communicating Alice and Bob. And they're communicating over a public channel where you assume that the contents of their messages are visible by other people. But you want those messages to be basically scrambled up so that people can't understand what they're sending to each other. Cryptography is also used for data verification, such as when you're downloading a file from the internet, you want to make sure that you've downloaded the correct file and it hasn't gotten corrupted somehow. And also used for authentication, so that you know that who you're talking to is who you intend to be talking to. So to start out with one of the most basic ciphers in classical cryptography, we have the Caesar cipher, which is probably something that many of you invented on your own back in grade school. When you would try to perhaps communicate with another person in your class by passing them notes, you want to make sure that the teacher can't intercept and know what you're saying. So what you'll do perhaps is you'll take the alphabet, and then instead of putting down the letter A, you might shift it over 3 spaces or something so that you're now putting down the letter X. And similarly, you do that for every single letter in the alphabet by that same shift. So here I'm trying to encrypt the word physics, and instead I would send my friend that jumbled mess of letters, and he's able to go backwards with that cipher and decode what I sent him. This is obviously pretty insecure, because as you send more and more messages, people that have access to this public channel can therefore do an analysis on the letter and the word frequency of your messages and figure out, what corresponds to the letter E, because that's the most frequent letter in the English alphabet, and etc. So it's not very effective, but if you're in a basic situation where you don't really need to send too many messages or something, it'll suffice. Here is a much more robust scheme called the one-time pad. And it was proven by Claude Shannon to be absolutely secure, so that people who have access to this public channel can't actually figure out what you're sending. The only information they actually get is just the maximum possible length of your message that you're sending to the recipient. However, unfortunately, this one-time pad is infeasible for most common use today, because the key that you're trying to use to encrypt your message is supposed to be completely random. It's like a bit string of zeros and ones that you're supposed to generate randomly. And most of the random number generators we use nowadays are actually pseudo-random, such that they actually rely on a function that, given some seed, will give you the same output. So typically those can be broken. The key also needs to be pre-shared between the two people who are communicating, Alice and Bob. And that presents a difficulty because usually they'll have to actually meet up in person. And if you're trying to communicate over the internet with someone you've never met before, you can't pre-share a key. The key also can never be reused, because at that point it can be compromised. And it has to be at least as long as the message, which is probably the least infeasible property of these. But the way the one-time pad actually works is that you have this bit string of zeros and ones, and you have your message, which you've converted into a string of zeros and ones. And what you do is you XOR your message with the key, which is basically just addition modulo 2. And so because Alice and Bob have the same key, Alice will encrypt her message using the XOR. She'll send this encrypted message to Bob, who will then take his key and XOR it with the encrypted message, and what will result is the initial message that Alice is trying to send. Because no one else has this key, it's completely secure. And as you see on the bottom right here, if you take any bit X, which is a 0 or 1 in your initial message, and you XOR it twice with 1 or with 0, you recover X. So the one-time pad is an example of something called symmetric key cryptography, where Alice and Bob, the two parties, use the same key for encryption and for decryption. You need to distribute this key securely to the other party which again presents one of the difficulties I discussed before for the one-time pad. But a solution that people use without actually having to meet up nowadays is Diffie-Hellman key exchange, and they also use the RSA cryptosystem to do this. Again, this is a disadvantage because you're sharing a key, like Alice and Bob are sharing a key, but if it's a third person, Charlie, Alice can't have the same key with Bob as with Charlie, because if she did it, whenever she would try and talk with Bob, Charlie could intercept the message, the encrypted message, and use the key to decode it, decrypt it. So you're going to need a key for each person, and for n people, if they're all trying to communicate with each other, it's going to scale as n squared, and that's a lot of keys. That's not a huge deal, like now that we have computers and stuff, but that is one disadvantage. So symmetric key cryptography, because it's not a big disadvantage, is used today in a form called Advanced Encryption Standard, AES, which allows your computer to talk to the internet with your web browser. So the way the Diffie-Hellman key exchange protocol works is it's a secure key distribution between the two parties, Alice and Bob, where each of them will pick a number, lowercase a and lowercase b, and they will keep these numbers private, and they won't share it over the public channel, and they won't share it with each other. And then publicly, they'll agree on a number p, which is a prime number, and it's typically a very large number and chosen randomly. And then they'll pick a number g, which is a generator of p, also known as a primitive root mod p. And basically what that means is that p is a prime number, so obviously no number is going to be able to multiply with another number and get p, but this number g can be exponentiated and then taken mod p, and it'll span the set of numbers between 1 and p minus 1. So because it generates every number in that range, g is a generator of p, and not every prime number is a generator for another prime number. So once you satisfy that generator requirement and you're picking them randomly, that's all you need. And then Alice and Bob will, privately using their lowercase a and b, they'll compute uppercase a and b using these functions right here, and they'll send that over to the public channel also. And you might think that because g is known and p is known, and then big A and big B are known, that little a and little b can be, like, the function can basically be inverted, and you can find little a and b. And that's actually not as easy as it seems. So the way the key generation actually works in Diffie-Hellman key exchange is that Alice will take the big B that has been shared by Bob, and Bob will similarly take the big A that's been shared by Alice, and they'll both exponentiate it to their private lower a and lower b. And then if you work out the math, you get this g to the AB mod p, which both of these reduce into, and that becomes their key. Obviously, this key can't be used as a message because Alice doesn't have control of what Bob picked as his little b, and Bob doesn't have control of Alice's little a. But it's still a secret key that they share because little a and little b are never publicly stated on this public channel. So the eavesdropper lacks this and can't compute the key. So they use that to encrypt their messages and decrypt their messages. So as I mentioned before, the math works because it relies on the little a and b not being very discoverable from knowledge of the public big a and b. And the way this works is that it's basically a one-way function, such that you can't invert it. And this example is the discrete logarithm problem. So with knowledge of, for example, big A, G, and P, you can basically only find A by just guessing and checking. Like there are some better algorithms, but they basically don't scale well. They're basically exponential with time. Okay, so the basically sister cryptographic protocol to symmetric key cryptography is asymmetric key cryptography. And rather than two people sharing the same key, as I mentioned before, every person is going to have different keys, but each person will have two keys. One of the keys they'll be able to use to encrypt messages and the other one to decrypt messages, but they can both do both functions so long as the same one is not encrypting and decrypting. So what you do is each person will take their two keys and they're going to publicly share one, and then everyone's going to know it's associated with them, and they're going to keep the other one hidden, and that's their private key. So to communicate with a person who has a public key and then a hidden private key, what you do is you take your message and you encrypt it using their public key, and then you know that only they can decrypt it because, as I said, one can encrypt and the other can decrypt, but one of the keys can't do both encryption and decryption. So you'll encrypt it with the public key and only they can decrypt it, so you know it's securely going to go to them. And then to authenticate, if I have a public and private key and I want to make sure everyone knows my message is coming from only me, I will basically sign it or encrypt it with my private key, and then everyone will see my public key and know that that's mine, and they can use that to decrypt the message, and because it works successfully, they'll know that I had to be the one who encrypted the message initially. So the example of this that is used most often is the RSA cryptosystem, which was developed by these three guys at MIT. And even though it can be used to exchange messages, which the Diffie-Hellman protocol cannot, it's primarily also used for symmetric key exchange, so then you can do symmetric cryptography between two parties. So to set up RSA, each person will need to choose two prime numbers, P and Q, and then multiply those together to get a composite number, and we call that M. You compute something called the totient function of n, which is very easy to do given p and q. It's just p minus 1 times q minus 1. And then you pick a number e co-prime with phi, the totient function. The whole mathematical reasoning behind this is kind of complex. I'm just giving a brief overview of what we do rather than explain all the inner workings of why we need phi of n. But after that, you're going to compute a multiplicative inverse d such that dE mod phi gives you 1. And basically the upshot is that d is going to be your private key along with p and q are privately held, and phi is privately held. And then n, your composite number of p and q, and e are your public keys. So to summarize, the first two lines are what I just said. And then if someone wants to encrypt a message and send it to you, they're going to look at your public n and e and raise their message to the e power, and then do modulo n. And they'll send that to you. And then you decrypt it by raising it to the d power and doing modulo n. And if you work through the math, you get that equals m, the message. So again, how does this math work? It relies on d not being easily discoverable from knowledge of the public e and n, where d was the multiplicative inverse of e. So in other words, this is another one-way function. But this one, rather than the discrete logarithm problem, focuses on the difficulty of prime factorization classically, which basically says with knowledge of n, it's very tough to find p and q, as long as p and q are very big. So after you do find p and q, however, finding phi and then d follows very quickly. So basically it just relies on the prime factorization, which is essentially guess and check, similar to the discrete logarithm problem. As you see here at the bottom, yesterday it actually came out in the news that there are these chipsets on some computers that are not choosing p and q randomly, and this is bad because once you analyze enough of these, you can figure out that there's like a certain method to picking p and q, and it becomes easy to compute d, and so anyone can decrypt the messages that were intended for you. And these also have big legal consequences. So now I'm going to transition into exploring the quantum regime. So as just a brief summary, the reason that classical computing is so often used for cryptography is because it uses bits of zeros and ones, and cryptographic schemes usually use zeros and ones. So in quantum computing, on the other hand, we use qubits, not bits, which have a state, let's say psi, which are a superposition of two orthogonal states, 0 and 1. And basically in quantum computing, although some of the gates that are available to us in classical computing are no longer available because all the gates have to be unitary for quantum circuits, we actually have that we can basically have a superposition over all of the possible solutions to our problem, and basically check which one works for quantum algorithms, and it basically allows us to work through the entire process with a set of solutions rather than trying each solution one at a time. That's the benefit of quantum computing. So as a proof of concept, there's something called Deutsch's algorithm, which presents like a quantum speed up over the classical case, which basically says if you have a black box function f, and it takes as an input a 0 or a 1, and it gives out a 0 or 1, you want to basically ask, is f reversible, which says, is f of 0 equal to f of 1? Because if they're not equal, then you know the outputs are either a 0 or a 1, but not like both 0, 0 and 0, 1. Like, for example, f of 0 could be 0 and f of 1 could be 1, or vice versa, but they can't be the same number. And if they are reversible, then they should be different. So how many steps do you have to do to determine reversibility? Well, classically, you need to do 2 steps. You need to check f of 0, and you need to check f of 1, and see if they're equal. But quantum mechanically, we can actually span the solution set and then work it through, and you actually only need 1 step to determine whether or not this function f is reversible. Then there's another example of a quantum speedup called Grover's algorithm, where you can search an unorganized list for a specific element, whereas classically, you expect to, in the worst case, search the entire list of n elements. With Grover's algorithm, you actually take the square root of n steps. The only difference here is between this algorithm and Deutsch's algorithm is that this algorithm is not deterministic. You only get the right answer a certain probability of the time. But what you can do is you can bound that probability by running the algorithm over and over. And that's actually just going to lower the chance of getting the wrong answer. And then you just do that until you're sufficiently content with the probability. Now, the big league here is Shor's algorithm. So Shor is a guy who's a Caltech alum. He has his BS from here. And in 1994, he basically published a paper that will eventually ruin the old protocols of RSA and Diffie-Hellman key exchange by factoring numbers, prime factoring numbers very quickly and taking discrete logarithms very quickly. So classically, again, we find these problems very hard in about exponential time, but with Shor's method, it's actually polynomial time, scaling with the size of the input. So although there may be classical factoring algorithms that are just as good, it suffices now, before quantum computers have been implemented, to use the RSA and Diffie-Hellman, but we're going to need a new key distribution protocol if we want to actually maintain our secure cryptographic communication. So back in 1984, Bennett and Broussard, two leaders in the field, came up with BB84 quantum key distribution protocol. And basically what it does is, in addition to using classical channels as before, it's going to use a quantum channel in order to send qubits between Alice and Bob, the two parties trying to communicate. So what happens is Alice will randomly pick a qubit in one of four states, 0 or 1, which are in the standard basis and orthogonal, and the plus and minus, which are in the Hadamard basis and orthogonal. And she's going to do this with equal probability. And she'll send a bunch of qubits to Bob, who, because he doesn't know what she's sending, he'll just choose a random basis, either the standard or the Hadamard basis, to measure these qubits. He has obviously a 50% chance of picking the same basis as Alice, so half of his answers will be, if she sent a 0 or 1, he measures in the plus minus basis, his answer will just be wrong by default. So after they do the measurements, after Bob measures and Alice sends, Alice will reveal what basis she used, and Bob will reveal what basis he measured in, and they're going to throw out the mismatches. So now they should be perfectly correlated and have exactly the correct measurements on both sides. But the issue is, so that they can use this as their key, as a symmetric key now. But the issue is that, what if there's an eavesdropper who's also making measurements before the qubit gets to Bob? So even when Alice and Bob pick the same basis, the eavesdropper might pick the wrong basis because they also don't know how to determine what basis it is. And that could actually collapse the qubit into the wrong state when Bob measures it. So for example, if Alice sends a 0, eavesdropper measures in the Hadamard basis and gets a plus, and then Bob measures it in the standard basis, he might get a 1. So even though they've agreed that they measured in the same basis, if there's an eavesdropper, they might get different outcomes. So what they'll do is they'll take a subset of their string of correctly basis measurements, and they'll check a few and throw out the ones, and throw them out. But they'll do that to ensure there was no eavesdropper. And if they don't get near 100% matching up, then they're going to know that they have to go through the protocol again over a more secure quantum channel. And they can then use this, because symmetric key classically is a one-time pad, which we've shown, or which Claude Shannon showed and I talked about, was provably secure. So there are other QKD protocols that have been invented since then to solve certain issues. One is called B92 that Bennett came up with 8 years later without the help of Broussard, which simplifies it by only using 2 states, the plus state and the 0 state, and these are obviously non-orthogonal. So the way it works is it starts out the same. It has BB84. Alice will choose a state randomly and send qubits to Bob in one of these random states. Bob will again choose a basis randomly and measure in a random basis. The key thing here is that rather than sharing what bases they use, they're going to share Bob's going to share when he got a 1 and when he got a minus. Because if he gets a 1, Alice could not have sent a 0 state. She had to send a plus state, and he measured in the wrong basis. And similarly, if he measures a minus, Alice could not have sent a plus. She must have sent a 0. So when he gets a 1 and a minus, he knows what basis she sent. So the basis is now the symmetric key, and his measurements, whether he got a 1 or a minus, are now the publicly expressed information. And they use the same protocol to detect whether there's an eavesdropper or not. So another protocol is called decoy state, which solves an issue with the experimental implication of BB84. And basically what happens is there's an attack on BB84 called photon number splitting. And usually in BB84, you assume that you're shooting photons, single photons from Alice to Bob. But in real applications, you're using a laser which is highly attenuated. So most of the packets only contain 0 or 1 photon, but some contain greater than 1. And if the eavesdropper suppresses the ones with 1 or less photons, and with the ones with greater than 1 photon, takes one of the photons and sends them on to Bob, then once they've expressed over the public channel what bases they used, then the eavesdropper can measure, and the eavesdropper will then have perfect, she won't have messed up their measurements and will have the exact symmetric key that they're going to be using. So this decoy state QKD solves this photon number splitting attack by basically just having Alice vary the intensity level with which she's sending these photon pulses. It basically makes it statistically computationally difficult for the eavesdropper. Now to move away a little bit from communication, cryptography for communication, we have something called bit commitment. And basically what bit commitment is if I go up to you and I say, I'm thinking of either 0 or I'm thinking of 1. And if you get what I'm thinking correct, I'll give you $50. So you can guess 0 and I'll tell you I thought 1. And you can guess 1 and I'll tell you I thought 0. Basically wherever you guess, I will never have to pay you $50. So you want a way to ensure that I'm actually telling the truth when I tell you you're wrong. So bit commitment solves this. Bit commitment basically says that I have to commit to a value before the reveal, and then that should be binding, and then it should also be hidden such that you can't see my value before I'm allowing you to check where it is. In 1996, they actually proved that bit commitment was provably insecure, which means that there is no way to have it rely on more than just hard math. It can always be broken because basically the binding property implies that it can't be hidden, and the hidden property implies that it can't be binding. And this is a bit of like a sad discovery, but they're used to make something called zero-knowledge proofs, which were actually shown to still be safe from quantum attacks, which is pretty relieving. But what zero-knowledge proofs are is basically I want to convince you that I know something without actually letting you, without actually giving you any of the information that I know, which seems almost like impossible. But an example is if you have two guys and one of them is colorblind and he's got a red ball and a green ball, but he's not sure that the colors are actually different, you can actually tell him that the colors are different without actually revealing to him which one is colored what color. So what you do is the colorblind guy will hold the two balls and he'll show you one, and then without saying anything first, he will turn around, pick another ball, and if he chooses, he can switch it. Like if he showed you the green ball, he can switch it for red or just show you the green ball again, but he'll show you a ball, and he'll know if he switched it, and he'll ask you if he switched it. If you get the answer right, you could be guessing, and you have a 50% chance of that anyway. But as he repeats the turning around and possibly switching the ball and presenting it to you again, and asking if you switched it, that's going to bound the error with which you're probably guessing, the chance with which you're probably guessing. So some of these zero-knowledge proofs actually rely on bit commitment, such that the guy who's proving, for example, proving what color, that he knows that there's different colors, it requires him to commit to a response before the reveal phase. So finally, I want to conclude just by giving an introduction to quantum networks, which are how we're going to communicate with qubits. So when there's a large distance between Alice and Bob, we've actually shown that the noise in between them as you're trying to transport the qubit will increase exponentially, and the fidelity of the qubit will be pretty low. And unlike classical bits, because there is this quantum no cloning theorem, you can't just make a bunch of copies of the qubit to amplify it and send that through the channel. So what we do instead, as proposed in '98, is have these things called quantum repeaters, evenly spaced between Alice and Bob. And these repeaters utilize quantum teleportation to send from Alice to the first repeater, one state, and then from that repeater to another repeater all the way down the line using quantum teleportation, and then finally to Bob. And this actually increases the fidelity a lot, rather than just one, like without this quantum repeaters set up. And additionally, these quantum networks will use quantum memory, which is a lot different from classical memory in your computer because it can't collapse the superposition while having to store the qubit. So to conclude, I hope to have shown you that quantum computers pose a threat to classical cryptography, and I also hope to have shown that there are solutions that take the form of quantum key distribution protocols. Additionally, I hope to have given you a brief introduction to quantum networks. So that concludes my discussion. Are there any questions? Marcus?
Yeah. Why does the noise grow exponentially in distance?
I just cited the result. I don't actually know the result, but
okay. Do you have any intuition for why that might be the case? Because I would think it would be more or is it like exponential distance or like distance to like some power?
I think you should check out this paper.
Okay.
I just cited what they were saying.
Sure.
This is the one in which they proposed quantum repeater. So I figured that they're going to give decent motivation to it.
Okay, comments? On the presentation per se?
I thought it was pretty clear. I thought you could spend more time on this last part, the quantum networks thing, I think. Seems more
Yeah, it
interesting.
might have been interesting to have more than a page on
Yeah.
Yeah.
it. Building up to it in some sense.
Yeah, it was really tough because there was so much I wanted to present on, and then as I started doing everything, I was like, well, I'm definitely going to run out of time if I.
Well, you actually took, what, 26 or 27 minutes.
Okay.
So.
And when I practiced, I was like 33. So.
Oh, really? I mean, you were talking at a good clip, but it didn't feel rushed or anything. In this class over the years, there have been lots and lots of discussions of quantum topics. And I thought this was both the most sophisticated explanation and the clearest. Really very good.
It's good to do both the classical and quantum examples, like a number of different examples, and explain them very clearly. Some people want to just jump into trying to explain Shor's algorithm or something like that, and they lose people right away. So I think your approach of choosing the really simple examples and explaining them clearly was good.
It's also the first one that hasn't had a blocks.
Yeah, I assume that either that was prior knowledge that they could
Yeah,
use,
no,
or
that wasn't a criticism.
Yeah.
In fact, you're right. But it is a fact. No, that was really good. It's not trivial material.
I think your slides could have really benefited from like figures and illustrations of these
Yeah,
different
that was-
protocols.
Maybe you need a blocks.
Just like showing where the different bits are moving and like each step of the way, what each person is doing and things like that. I think it would have really benefited rather than just listing it in text.
One can actually probably make some sort of animations. with
Yeah.
Things
Yeah.
moving around, which would be illustrative. Has anybody done something? Somebody made it.
I can look into it.
No, that was,
Thank you.
okay. So you also are 16 by 9 guy.
Yeah, that's just the default of what my computer.
No, I mean, most projectors are still 4 by 3.
Okay.
But increasingly, people are doing this and projectors are changing. So eventually, they
Yeah.
come to some equilibrium. I mean, the only thing that happens is you don't use, when you have this aspect ratio and the projector has a different one, you're just not using all bits.
Right. That's why I tried to make the font legible enough.
No, I think it was quite legible. What size font?
The big ones are 28, and then the indents are 24.
Yeah, no, that was very good. Okay, great.